Hello, everybody. Good afternoon, good evening, good morning, wherever you are in whatever part of the world. And a warm welcome to eMumba's presentation today on how to use using DPDK for an ultra-low latency application. My name is Ali Rizvi. I'm the head of R&D at eMumba, and my co-presenter today is Ahmad. He's a senior design engineer at eMumba, and you can reach us at acceleratorsoftware@emumba.com. So let's dive into the agenda for today. We're going to walk you through our low latency story, how we came to DPDK to solve the low latency problem. We'll talk about an algorithmic trading application that was what drove us to dig deep and find solutions for latency. And as we go through that, we'll talk about where does latency hide in such an application and the analogy for other similar use cases over there. Next is network stack latency optimization, which is probably the most important part or the most interesting part for all of you guys to see how we got to the kinds of numbers we were able to achieve with DPDK. And next is some numbers, latency versus throughput performance results. So we have some numbers here that we're going to share with you guys. And I'm sure you'll have many questions around that. Feel free to put them in the chat. We have Talal from the team and Sarosh, I believe, also, and they can help with the questions, and we'll take questions at the end once we're done with the presentation, hopefully on time. Next up is sort of continuing our story. Since we're building an application using DPDK, we did need a low latency user space stack. So we'll talk about that, and we round it out with talking about our future contribution ideas, how we plan to upstream the stuff that we've done, the results that we've achieved, how we sort of make it more accessible for the community. So let's get started here. Our low latency story is, like I said, is around acceleration of a trading application. These applications are notorious for their low latency requirements. I mean, as they say in the trading world, microseconds are dollars. And as we were working to solve this problem, we found that it's actually nanoseconds, because you can find tens of nanoseconds worth of optimization opportunities here and there that help you get to your latency milestones. So let me sort of lay out what an algorithmic trading application looks like and the part that we worked on. So if you look at the picture here, there's the exchange at the bottom, and then there's the application or the trading system running in a co-location facility geographically close to the trading venue or to the exchange. It's sometimes hardware, but mostly it's software running in co-location. And the exchange sends out market data as in multicast fashion to the application. The packet has to make its way all through the application. There's the stack, the feed handler, the business logic, the order entry gateway, and the response goes out back to the exchange or to the venue as a TCP message. So as we drill down a little bit deeper, where does latency hide in such an application? So the blocks highlighted in blue here are the ones that we worked on, the feed handler and the stack, trying to optimize those for latency. So there's two major pieces here, and I'll talk about the application first. With the application, what the feed handler does is it's supposed to extract the critical insights or useful information from the messaging coming from the venue and normalize that and send it across an API to the business logic that in turn makes decisions of what kind of trade it wants to place or not place, and hand it over to the order entry, which in turn packetizes it as per the protocol and sends it out as a TCP message. So this is a UDP to TCP message, and everything happening here in this entire pipeline has to happen as fast as possible. So what's important for you to measure in these applications and such latency critical applications is wire-to-wire latency. So focusing in on the feed handler, we built the application, we were measuring performance, but we were nowhere close. I mean, we did some we started off with a multi-threaded architecture. It looked much more scalable, but we were able, the best we could do was 3 microseconds at the median with that application, the socket to API, just the application, focusing on just the application. And then, but we had to, but it was sort of nowhere close to where we needed to be. So we dug deep and we learned quite a bit from the open source community, from CPPCon. A big shout out to the folks at CPPCon, many good engineers coming there, sharing their insights. That was tremendously useful for us. And so we did lots of good sense optimizations. Like we moved to a single thread architecture that was the biggest plus, that helped a lot. We did cache alignment, cache line packing, hot path optimization, memory pre-allocation, no copy, core isolation, thread pinning, all of those good things. And so all of these are kind of, they don't lock you into any particular architecture. With those, we were able to get to 100 nanoseconds at the median for the application. This is for the Chicago Mercantile Exchange. And so the application optimization, even though it's a very interesting part of the story, but for today's talk, that's not going to be the focus. We're going to focus more on the network stack latency, because once we were done with that, we knew along the way that the biggest latency pole by far was within the network stack. Out of the box, Linux was giving us 50 microseconds round trip. And another thing I want to highlight here is, for these applications, not just the median, because when you're trading for this kind of an application or other critical latency critical applications, you don't have to be fast as far as where your median lies. But it's a very narrow window of opportunity, and it's day by day it's shrinking as people get faster and faster. So you have to fall more often, on average, more and more within that window. So it's not just latency that's important; it's also your standard deviation, not just your median. And so the important part, or the most interesting part of our journey to achieve our goals, was network stack latency optimization to achieve our critical milestones. And like I said, we were 50 microseconds out of the box. We tried to do stuff like packet mmap. We used packet mmap. We used flow steering, but we were still nowhere close. And we quickly found out that we needed to do some kind of kernel bypass or stack bypass with stuff like OpenOnload from Solarflare. So we chose DPDK. DPDK was kind of like a no-brainer for us. It's open source, off the shelf, reliable, stable, globally deployed. If you have to do anything with accelerated data plane, or DPDK is sort of a go-to solution. So we chose DPDK, and so you get core isolation with that, and all of those things. And then together with that, we used Interflow Director to steer package directly to our application, which is sort of the logical next step once you've done core isolation. And we had some amazing results. We cut down the latency in half, like from 50 to 26 microseconds. Now, even though as amazing as that sounds, going from 50 to 26 microseconds, so now we knew we had the major building blocks of a solution in place, but we were still nowhere close to what these applications need. So on to step 2. So we knew that we needed to dig a little deeper, go inside DPDK and try to tune things and see whether we could get to our goals. And what you see, like when you look at DPDK, you can quickly see that batch processing is sort of the workhorse in DPDK, and rightfully so. It works really well for a throughput first criteria. But for ultra low latency, we quickly saw that there is room to make a trade-off between batch processing and scalar processing. And that's exactly what we did. Even though we had intrinsics turned on, tried to make the best use of vector processing, we weren't really getting down to the levels we needed. So once we used scalar mode, we got from 26 microseconds down to 5.1 microseconds. Now, this is a 5x improvement on DPD with just DPDK. Out of the box, DPDK was 26 microseconds. We got to 5.1 microseconds doing those kinds of trade-offs. But so this is the point at which we are getting within striking distance of commercially available low latency solutions, but you still have a ways to go. And in tandem with this, the next step, or step 3, is where things get harder and harder, trying to hit your latency goals. It's incrementally, I mean, exponentially gets more difficult. And so that brought us up to step number 3, network stack optimization, step number 3. And I'll hand over to Ahmed to explain what we did in step 3.
Thank you, Ali. Although moving, can you please go to the next slide? So, although moving to the scalar mode gave us a big improvement in the latency, but that was not enough for our application. So we decided to move to the code and decided to optimize the data path. We did some optimization on the receive side as well as some optimization on the transmit side. On the receive side, we observed that the PMDs still do some kind of batching even in the scalar mode. And if, for example, PMDs look ahead for some fixed number of descriptor, even if we request for one packet from the application. So we started with some experimentation and tuned that look ahead in such a way that it gives us the best latency without compromising the throughput. Secondly, we moved to the transmit side. The data from the transmit side from the fetching of the descriptor. So we tuned the prefetching in such a way that the NIC always prefetch from the NIC, even if there is one free descriptor available in the hardware. Similarly, we tuned the write back in such a way that it write back the descriptor as soon as possible to the host machine. These things help us improving the latency above 1.4 million PPS. After doing this step, we was at 3.6 microseconds from 5.1 microseconds.
Right. So, as amazing as this number is, what's even more amazing is that this is we achieved this on Intel's 82599. These numbers are in the ballpark of what you get with commercial specialized low latency NICs, and which are like 20 times the price of an 82599. So this is, I mean, the numbers are even more impressive when you consider how the platform is all, I mean, off-the-shelf hardware. So next up, we're going to present some numbers and results that we've seen. This is perhaps the most interesting part for all of you interested in this kind of work. And we'd encourage you to put your questions in the chat. And there's people from the team over there, and we'll try to take as many of the questions as possible once we're done with the presentation. So Ahmed, please go ahead and let's walk everybody through the numbers we've got.
So you can't fix what you can't measure. We do not have access to the expensive traffic generator like Ixia, so we built our own setup. Let me walk you through our latency setup, which we are very proud of. So on the right side, you can see a traffic generator. So this is a DPDK based traffic generator. We are using a slightly modified version of packet gen. We put a unique sequence number in each packet and forward it to our SUT. Our SUT is based on D2166NT, which is designed for edge compute. It's running an L2 forward application, so it forwards each packet with a unique identifier back to the packet generator. In between, we have a fiber tap. We use this fiber tap to timestamp every packet going and coming back from the SUT. Our timestamp server can timestamp within a 7 nanosecond precision. We compare both the packets, coming packets and the outgoing packets, and get our latency measurement. This system mimics stack T1, which is widely accepted in algo trading industry. This is remotely deployable and operable for URL application measurement.
Right, and so what I'd like to emphasize here that you just can't fix what you can't measure. So So this is sort of like a homegrown setup. It does wire-to-wire using fiber taps. There's an independent observer machine. We're able to get 7 nanosecond precision hardware timestamping. So we don't have fancy Ixia or Corvil type of equipment in-house. This is all built on COTS hardware and remotely deployable and operable. And all of the numbers that we're going to show you next have been the measurements have been done using this system. So go ahead, Ahmed. Yeah.
So this is the latency measurement we have got after the optimization on 82599. We have throughput on the x-axis. Although our application do not require high throughput, but we have go all the way to the 10 gig. On the y-axis, we have latency in microseconds, and the different line represent different packet sizes. We have gone from 64 bytes to 1024 bytes. We were able to get our measurements in very narrow band of 64 to 192 nanoseconds. Here I'm talking about 128 byte packet size because it's well suited for our use case. Our latency was within 500 nanoseconds of the median, and we have got numbers up to 99.99 percentile, and our latency was within 2 microseconds of the median.
So I mean, there's a couple of noteworthy things here. This is L2 forward with 82599, and the standard deviation, like Ahmed just mentioned, the standard deviation when we sweep packet sizes and we are sweeping through PPS. So we want to go from the lower PPS all the way up to 10 gigs, give you sort of numbers all the way up to 10 gigs throughput. The standard deviation stays within this narrow band of 62 to 196 nanoseconds, and as we sweep the throughput, the median is like within 500 nanoseconds of where you have the best median latency. And so these two aspects. So this is what you need for an algo trading grade system. And we are able to deliver that with 825. And obviously, I mean, the commercial specialized solutions are a little bit better than this, but yeah, doing this with 82599 is the amazing part. So we also did the same thing for X722, and Ahmed can guide you through what we saw there.
So we did the similar experiments with X722, but to our surprise, we got a spike when the PPS was low. On our investigation, we found that this is due to the interrupt moderation, because this is how the X722 is designed. We disabled that interrupt moderation and saw some good latency numbers. Ali, can you please go to the next slide? So here you can see our measurements after disabling interrupt moderation. The one with the dotted lines are before disabling the interrupt moderation, and one with the solid lines are with interrupt moderation. So our latency was significantly reduced. Can you please go to the next slide, please? So this is the zoomed in version of the similar graph we got after disabling the interrupt moderation. Our latency was significantly reduced, but it is still not better than the latency we have got with 82599. Also, the standard deviation is above the 82599. We are also seeing some ups and downs in the latency, and we are still investigating why we are getting these ups and downs in the latency.
Right. So with X722, we hit a problem. We found a workaround. Interrupt moderation was causing that, and that's also, so we get pretty decent numbers. But you see here that the lower PPS and the latency jumping up and down. So that's something we're investigating, trying to get a handle on, and would love to collaborate with you guys, with Dave and Reshma before us. I mean, you presented numbers with X722, so we like to learn from the driver community and figure out how to improve things further. And so our story continues. That's our numbers, but we needed a low latency user space stack. So you're building an application on top of DPDK, you do need a user space stack, a low latency user space stack, and we chose FStack, and Ahmed can sort of guide you through how all of that happened.
So after looking at different user space stacks, we shortlisted the FStack because it's an open source based on FreeBSD 11.01. It's very easy to use. It has APIs which are very much similar to the POSIX. Also, it's very much reliable, and we can see that it can support up to 10 million concurrent connections, which is well aligned with the 3D requirements. So when we started with the FStack, its latency was 3 microseconds. We also started to tune the FStack and found that it was also doing some batching to favor throughput. We tuned that FStack, and then we discussed our recommendation with the FStack community, and thanks to them, they uploaded our recommendation on their GitHub repo. So now after the tuning, we are at 9 microseconds from 6 microseconds.
Right, so we got to like below a microsecond, 0.9 microseconds, and again, open source at work. We made a suggestion, they upstream that, and that solved our problem, and hopefully also for others. So that rounds out our story. We and low latency, and that leads us to. You can see parallel with this low latency application for other ultra low latency applications where you have some critical information carried in each and every packet, and you want to process that and react to that information as fast as possible. So you probably don't care that much about throughput. We do care about throughput, but then how much is that? And so our future contribution ideas, before we sort of go into those at a higher level, I wanted to sort of quickly give you a picture of what kind, when you talk about low latency, what are the usage scenarios? And this is from the 5G standardization, the IMT 2020 standard, where they have this nice diagram coming straight out of their documentation. So this triangle is laying out latency versus throughput profiles or use cases, grouping them. So at each vertex, there's a different latency versus throughput trade-off. So at bottom right, you have the ultra-reliable low latency communication needs, like a millisecond or low. That's for self-driving cars and other mission-critical applications where they're trying to communicate, a self-driving car trying to communicate with the infrastructure to get critical insights quickly, communicating back and forth. And then up top, you have applications like immersive AR, VR, 3D video, 3D gaming on the edge, which do care about latency, maybe in the tens of milliseconds, but then also need decent bandwidth. And at the bottom left, you have the massive machine type communications. That's your smart cities, smart manufacturing, which do care about latency, but they need a lot more connection density, so like 1 million connections per kilometer square. So with that as inspiration, how we're planning to upstream our work is as follows. Like, so what do we plan to do? We plan to export high-level, low-latency config so that users don't have to worry about tuning arcane sizes and thresholds to meet their requirements. And how do we plan to do that? We want to use latency super parameters to help select the required latency versus throughput profile, for instance, like the IMT 2020 usage profile that you saw. So you have a good way to just select which profile your application lies in, you build your application and deploy it. And looking even further out from that, down the line, we would want to make that API driven so that the service requirements for applications can be met in a programmatic fashion. So that's our contribution. We already we've become part of the past 6 months or so. We've been contributing. We've been using DPDK for a year and a half now. So we're not just users. We've become contributors. And eMumba was mentioned on DPDK announced for these past 2 releases, 20.05, 20.08, and the collaboration continues. In the low latency space with 5G around the corner, the possibilities are endless. There's IoT where you have a tight loop, like a sensor actuator loop through the cloud. you have immersive AR, VR, even mobile electronic trading, smart manufacturing, smart cities, autonomous vehicle networks. All of those possibilities are there. And at eMumba, we're really looking forward to work with the community in the low latency space. And your questions are welcome. And we do have, that's all we had to present today. And let's take some questions from the audience. I will, so let me stop sharing the deck here.
So we have a question that I see 99.99 percentile. Do you measure the maximum latency? Yes, we do measure the maximum latency. And it was, as I have mentioned, that it was not much. And the graphs do have the maximum latency in them. So let me see. We have maximum number for 6722. For the maximum number for X722 was 9.067 microsecond on 128 byte packet, and the maximum number for 82599 was 8.1 microsecond at 128 byte packet.
IOMMU on latency. Do we have any, Ahmed or Talal, if...
Yes, we use the IGP QIO. We are not sure about IMMU latency. Now, moving toward the other question, we have a question that can you explain more about timestamp server? So we have a server which has a Solarflare card which takes latency measurement up to 7 nanoseconds, and they are hardware timestamps. So the timestamp do not get affected by the kernel jitter or stack. So the timestamp is taken in the hardware, and then it gets into the we record that PCAP, and then after that we measure the latency.
Right. I mean, some nice suggestions from Thomas there. Yeah, we've taken note of that. And yeah, I think we're almost out of time here, and we'll join the low latency track and continue discussion over there. Thank you all for joining and listening to eMumba's presentation today. Bye now.
Bye bye.